Hello, we will be presenting our paper with ID number 11322. The main motivation behind this work is that we provide a privacy transformation method that is able to protect speech signals against unwanted attribute inference attacks on voice biometrics, namely on gender and identity. At the same time, we aim to maintain the performance of the automatic speech recognition task and maximize the utility of the resulting privacy transformed signal. We also want to quantify the relationship between gender and identity information and determine if by considering only gender information, we are able to conceal much of the identity information embedded in speech. The main contribution of our paper is that we synthesize gender-ambiguous voices that are able to convey the content of speech, as well as at the same time protect the gender and the identity of the speaker against unwanted attribute inference attacks. We consider objectives concerning the privacy and the utility. First, consider an original waveform denoted by X and its associated gender Y, where we consider binary encoding for gender into a male or female. Following the privacy transformation method, we obtain the transformed waveform X prime and its associated gender Y prime that is non-binary or gender ambiguous. For the utility objective, we consider the automatic speech recognition task, that is the transcription of speech into text, and wish to maintain the performance of this task as unaffected as possible from the privacy transformation. For the privacy, we consider two objectives. First, we consider that an attacker would want to infer the gender of the speaker by applying binary classification on speech signal and classifying into male or female. We also consider the speaker verification task when an enrollment utterance belonging to an initial speaker is compared against trial utterances from speakers in the set in order to verify the identity of the speaker. Therefore, our objective is to be able to reduce the ability of an attacker to be able to infer the gender and verify identity of the speaker given the anonymized utterances. To this end, we propose a generative adversarial network that will be able to synthesize gender-ambiguous voices in order to protect mainly the gender of the speaker and by extent the identity of the speaker. The pipeline can be shown below. And the first step, we consider as pre-processing the conversion from the time waveform X into a MEL spectrogram M by applying the fast Fourier transform with 1024 beans and a sampling rate of 22 kilohertz, which results into a MEL spectrogram M with 80 MEL bands. The generator that has the task to synthesize a privacy transformed version of the original MEL spectrogram M outputs a synthesized MEL spectrogram M prime. This MEL spectrogram M prime, along with the original MEL spectrogram M, are inputted into the discriminator, which has the task to differentiate between the real and fake data and output a prediction given the original input M or the synthesized MEL spectrogram M prime. The last stage of the pipeline involves the spectrogram inversion operation, where we use a pre-trained neural vocoder that is able to convert a MEL spectrogram back to the time domain to obtain the privacy transformed time waveform denoted by X prime and associated gender Y prime, which is non-binary or gender ambiguous. For the synthesis task, we consider the generator, which has the task to generate gender ambiguous voices. The input into the generator is the original MEL spectrogram M, along with non-binary or synthetic gender labels, YN. that we sample from a Gaussian distribution of mean of 0.5 and variance of 0.005, such that the values sampled are close to the neutral gender label of 0.5 and do not overlap with the binary labels for gender of male and female. In that way, the generator can synthesize a transformed version of the male spectrogram given the new labels such that it is neither male nor female. We also insert a noise vector Z that is sampled from a standard normal Gaussian distribution of mean 0 and standard deviation of 1 that is inserted at the bottleneck of the generator, which has a UNet architecture, and specifically at the meeting point of the contracting path with the expanding path. This is used in order to increase the variability in the signal reconstruction and synthesize new voices that are sufficiently different from the original one. In order to optimize our model, we consider losses for utility and for privacy. In utility, we are interested in minimizing the distortion in the resulting signal, and therefore we use the mean square error between the original Mel spectrogram M and the privacy transformed Mel spectrogram M prime. For the privacy losses, we consider the cross entropy between the ground truth gender and prediction of discriminator given real and fake data, YR and YF. We also consider the loss, the cross entropy between the synthetic non-binary gender labels and the prediction of discriminator given fake data. The generator loss consists in the sum of the distortion loss with the privacy loss of the ground truth gender and the prediction of discriminator given fake data, such that the generator is able to reconstruct or synthesize voices that are gender ambiguous and learns a neutral gender. As these two objectives are competing and in minimizing the distortion while maximizing the privacy protection for the gender attribute, we use a constant epsilon that is between 0 and 1 and represents this utility budget in order to tune between the distortion and the privacy protection. The discriminator loss consists in the sum of the cross entropy between ground truth gender and prediction of discriminator given real data in order to learn the real gender of the speech given real data, and the privacy loss between synthetic non-binary gender labels with respect to the prediction of discriminator given fake data to be able to recognize the gender ambiguous gender. In that way, we are the discriminator is informed and is able to produce informed decisions given the data real or fake that is inserted to it. Let us hear some audio samples. First, for a female speaker, in the original sample.
And then we insist upon it, the study of social deformities and infirmities, and the task of pointing them out with a view to remedy, is not a business in which choice is permitted.
And now a compared model, the PC-GenGAN.
And then we insist upon it, the study of social deformities and infirmities, and the task of pointing them out with a view to remedy, is not a business in which choice is permitted.
And our model, the GenGAN.
And then we insist upon it, the study of social deformities and infirmities, and the task of pointing them out with a view to remedy, is not a business in which choice is permitted.
We can see that our GenGAN model is able to produce highest resolution spectrographs with respect to PC-GenGAN and have a lowest distortion inserted in the signal. Let us hear to a male sample as well, the original sample.
Take your place and let us see what the crystal can show to you.
And now for the compared model, the PC-GenGAN.
Take your place and let us see what the crystal can show to you.
And for our GenGAN model,
Take your place and let us see what the crystal can show to you.
we can see that for male speakers, there is a increasing high formant frequencies, and induces some distortion into the transform signal, denoting less effective into male speakers. To assess our results, we use the performance metrics for utility and privacy. For utility, we consider the word accuracy metric instead of the word error rate in order to assess the correct transcription accuracy. Therefore, a value of 100 for the word accuracy would denote the highest performance possible in speech recognition task with no transcription errors. For privacy, as we are interested from the discrepancy from the 50% accuracy value that denotes low confidence in the classifier's prediction in recognizing the gender or verifying the identity of a speaker, we introduce the normalized gender recognition and the normalized equal error rate that are normalization of the standard gender recognition and equal error rate measures. For both normalized measures, a value of 100 would denote the highest level of privacy protection possible. We compare our results with respect to state-of-the-art models that consider gender as an attribute to protect in a privacy-preserving scenario. All results from the models are evaluated on the LibriSpeech test clean set. Let us look at the original signal, which shows high utility and low privacy. We also append results for the GenGAN vocoder in order to assess the distortion that is inserted in the signal by the sheer operation of spectrogram inversion of going frequency domain back to time domain. As we can see, the utility is slightly degraded while the privacy is also impacted. As we consider three models from the state-of-the-art to compare with, the first two models, client hybrid and VQVAE gen model, the results are taken from the literature. And we can see that especially for VQVAE gen, the performance on the privacy task, both in terms of gender recognition and speaker verification, are very high. However, there is a very significant deterioration in utility that makes the resulting signal non-useful for the downstream tasks of speech recognition. We train and test the PCML-GAN model and of course our GenGAN model, which is a simple version of the PCML-GAN without the filtering process. We can see, although both methods are comparable in terms of privacy, and although PCML-GAN outperforms in terms of speaker verification, the PCML-GAN has a significant degradation in terms of utility with respect to our GenGAN model. Therefore, our GenGAN model provides the best privacy utility trade-off amongst compared methods. Also, the value for the normalized equal error rate for the GenGAN shows that by considering only gender information in our training pipeline, we are able to conceal much of the identity information embedded in speech. However, some residual speaker information is still present in the privacy transformed signal. We plot our results with respect to the privacy measures, the normalized equal error rate and normalized gender recognition, as well as with respect to the utility for the word accuracy, where both with all metrics value 100 denotes the highest performance. Therefore, the best performing models are shown in the top right corner. As we can see, our GenGAN model outperforms current methods and provides the best privacy utility trade-off. In conclusion, we have seen that we are able to synthesize gender-ambiguous voices in order to perform on the speech recognition task and conceal gender information. A model provides an improved privacy utility trade-off with respect to compared methods. And we have also shown that gender information is able to conceal much of the identity information of a speaker. Future work will involve improving signal reconstruction without degrading privacy and assessing naturalness of generated voices with subjective evaluation. Thank you for your attention.